OPSO. The title of the talk is Clark Measures and Composition Operators in Several Variables. Speaker is Professor Evgueni Doubtsov. You have 50 minutes and 10 minutes for questions. You are welcome, please.
Okay. So first of all, I would like to thank the organizers for the invitation to give a talk here. And also, I should mention that most of the results are obtained jointly with Professor Alexey Borisovich Alexandrov. So, and also I should mention that, the main point about this talk is several variables. So in one variable, those objects, Clark measures and their relations with composition operators by now are already well understood. So the main point is to get through difficulties in several complex variables. And I start with basic definitions. So Bn is the open unit ball of Cn, so n is allowed to be equal to 1. But in this case, usually I'll use a different notation. So as usual, D is the unit disk and T is the unit circle. And I'll consider a somewhat more general case than just the unit ball. So I consider a domain omega. This is a product of k copies of, in general, different balls in different dimensions. So Bn1 times Bn2 dots times Bnk. So the main point is to cover two basic cases. The first one is just the unit ball Bn, and the second is the polydisk dk in this notation. Actually, what is important that there is a difference between the unit ball and the polydisk. Well, from the complex analysis point of view, it's obvious, but even in this setting of more separator theory fitting, it will be visible at some points that they are different. But the main theorem holds for both objects. Just the result does not change if you consider the unit ball or the unit polydisk. And moreover, it holds in this more or less general setting of the domain omega under consideration. So also I'll denote by d omega the so-called distinguished boundary. So in this case, just this is a product of the spheres, the boundary of the ball Bn1. So this is the sphere, unit sphere in Cn1 and times other spheres. So this is not a topological boundary, but so-called distinguished boundary. And it is well known that, say, in the case of the polydisk, this is the right object to consider if you want to develop certain theory like Cauchy integrals, Poisson integral. So this is the right boundary where the function and the corresponding kernel should be defined. Okay, so now I need the notion of the Cauchy kernel. Well, more or less in this case, everything is explicit. So just I recall the explicit expressions for the corresponding Cauchy kernel. So C of Z zeta, this is C omega. It depends on, of course, on the domain omega. So for a point in the domain Z1, Z2 dots Zk, so this is just a product of the corresponding Cauchy kernels for the unit balls of domains in C and J. So if we consider just one unit ball, this is just the classical Cauchy kernel for the unit ball. If n is equal to 1 and k is equal to 1, we obtain just the unit disk. So this is the most classical Cauchy kernel for the unit disk. And also, just to make sure that we understand what happens, for the polydisk, we have k copies of cache kernels in the unit disk. So the variables are just the zj and zj, and n sub j is equal to 1 for every copy. And we just multiply the usual cache kernels, but with different variables, of course, for the unit disks. Okay, and well, the main kernel I'm going to use to introduce the corresponding, say, in particular, Clark measures. This is the corresponding Poisson kernel, and the main point here is that the formula is the same for the unit ball, unit disk, and the corresponding finite products. And well, I'll just mention just once this notion. This is the notion of the so-called bounded symmetric domain. Up to a certain generality, the same formula for the Poisson kernel still works. So this is, if we know the cache kernel, so the corresponding Poisson kernel is just this C of z, zeta times C of zeta z over C of zz. So z is a point in the domain, and zeta is a point on this boundary. I call this the so-called distinguished boundary. If we consider just the unit ball, this kernel is well known, but this is not the standard, say, real Poisson kernel, because, well, Bn is just the unit ball in R2n. So we already have the most standard and classical Poisson kernel, real Poisson kernel. This is a different one from the, since we have a complex structure, this is the most natural, actually. So the real one is not so useful. And this is so-called Möbius harmonic Poisson kernel for the unit ball. If we consider the polydisk decay, then we obtain so-called K harmonic Poisson kernel. This one is, well, essentially the only one, the only useful Poisson kernel in the polydisk, so there is no difference here. Okay, so the only point is about the uniball, but, well, as I said before, from the complex analysis point of view, it's well known that this is the right one. Okay, so now I'll also use the notion of so-called pluriharmonic measures and the corresponding set capital P, capital M, just pluriharmonic. Those are not the measures from the pluripotential theory, whatever it means, but just the definition is quite straightforward and simple. Once we know the, once we have the Poisson kernel in our domain, so we consider a measure mu, just a barrel measure on the distinguished boundary, and we say that this is a pluriharmonic measure, and write m in Pm of d omega, if and only if the Poisson kernel, so just the usual one, just once we know the kernel, we know what the Poisson integral is. This is a pluriharmonic function. Just to make sure that the word pluriharmonic is clear. Okay, in the unit disk, this is just a harmonic function, so there is no restriction at all. Okay, if we have several variables, then it means that this is the real part of a holomorphic function. So this is exactly why in the unit disk there is no restriction. So every harmonic function is the real part of a holomorphic function. If you have at least two variables, this is of course a restriction. But, well, if the measure is real, the Poisson kernel is real, and just this is the real part of a holomorphic function. Well, if the measure is not real, then just we can impose these restrictions on both the real and the imaginary parts of the corresponding function P of mu of z. Okay, and also in the case of the polydisk, we do have classical Fourier coefficients, well, not on the circle, but on the torus of dimension k. And in this case, just it's straightforward to write down the restriction in terms of the Fourier coefficients. It means that the Fourier coefficients are equal to 0 outside of the set z plus to the k, union with the corresponding reflection minus z plus to the k. So, well, the larger dimension, the smaller this part of non-zero Fourier coefficients. Of course, if k is equal to 1, there is no restriction. We just obtain the whole set of integers. But already in dimension 2, we have only 2 quadrants, the first one and the third one. And well, if k is sufficiently large, so we still have 2 small parts, and the rest 2 to the k minus 2, say, like quadrant-like sets should not support Fourier coefficient of this measure. So, well, at least on the polydisk, it's completely clear what it means. But anyway, even in the ball, well, there are also certain so-called HPQ projections instead of Fourier coefficients. Also, in terms of Fourier analysis, it is by now straightforward to write down the restriction and to describe those Fourier harmonic measures. Well, I'm not going to use this notion directly, but the main objects, Clark measures, will be of this type. So, well, I believe that I should explain that, well, these measures in several variables are somewhat more specific than the usual Clark measures on the unit circle. Okay, now I'm moving to the definition of the Clark measures, and also I think that I should give, well, before the main theorem. So the title refers to the Clark measures in composition operators, but well, somehow I think that well, besides the definition of these measures, I should mention at least certain interesting properties. Not all of them are directly used in the proof, but well, just to make sure that to make it understandable that such objects, even in several variables, in the classical case of the unit disk, it is well known that these measures are, say, maybe not omnipresent, but are useful in rather different situations. And well, the main idea of this part 2 is to just give a few examples of this usefulness of the Clark measures in several variables also. So I start with the definition. So we fix a point on the unit circle, and we consider a holomorphic function defined on our domain omega. So if you prefer, you can think about the unit ball of the polydisk. So the values of this function in the unit disk. So in the classical situation, this is just the holomorphic self-map of the unit disk. And we consider the quotient 1 minus modulus f of z squared over modulus of alpha minus phi of z squared. And this is not just a random quotient. This is the real part of the following quotient alpha plus phi over alpha minus phi. So, well, just this is an identity for complex numbers. If we replace phi of z by any complex number, say w in the disk, this is true. We just compute the real part and just in the straightforward way, and we obtain the left-hand side. Well, the main point is that the left-hand side is positive, definitely, and the right-hand side is definitely pluriharmonic, because just by the very definition, as I said before, this is the quotient is the holomorphic function, of course, because P is less than 1, its modulus is less than 1. So everything is fine, and no singularities. So and this is the real part of a holomorphic function. So this is a pluriharmonic function. Once we have a positive and pluriharmonic function in this domain omega, just basic theory like in the unit disk of Poisson integrals guarantees that there exists a unique positive measure, and we denote it by sigma sub alpha. This is sigma alpha of P, of course, and this is a measure on the distinguished boundary, so such that its Poisson integral is exactly our function. So just I prefer to write that this is the real part of this quotient, so the right-hand side expression. And just once we have this, of course, this is a pluriharmonic measure, so we have certain restrictions on its, say, spectrum, Fourier spectrum in the classical sense on the holodisk or the torus, and just in terms of, say, abstract harmonic analysis on the unit ball, or just the general domain omega under consideration. Well, these measures sigma alpha, as I already said before, once when they are defined on the unit circle, they were introduced, well, basically by Clark in 1972, but also at least several well-known mathematicians have been working on these objects essentially at the same time. Also, in particular, Donald Sarson has obtained a number of results on these measures. And well, somehow in the definition, I have mentioned that these measures are called Clark measures, and also, at least in the, say, United States literature, they also called AC measures, or even just directly Alexandrov measures. But, well, as I said before, also there are numerous results of Sarson on these objects. And, well, more later, Alexei Poltoratsky has obtained even more interesting results and applications of this object. So, well, but anyway, during this talk, I will say that the measures under considerations, those measures, sigma alpha, are just Clark measures in one variable or in several variables as well. Okay, so I mentioned here that these measures are classical, well, up to, say, at least for 50 years, they've been investigated and applied in various situations. And here I give several examples in several variables. So initially, the study of these measures, the studies of these measures were motivated by the corresponding so-called model spaces, and such spaces are defined in terms of so-called inner functions. So let sigma capital denote the normalized Lebesgue measure on the boundary. Still on the domain omega, we consider a holomorphic function defined on this domain and mapping omega into the unit disk. We say that this function is inner if its boundary values are equal to 1, sigma almost everywhere. Well, of course, it is well known that the boundary values, the radial limits, say, do exist almost everywhere, so everything is fine, is correct. And so we just write capital I of zeta for the radial limit capital I of R zeta. Okay. Well, because everything happens in this definition as sigma almost everywhere. Well, once we have an inner function, we write the corresponding Poisson integral for the sigma alphas. This sigma alpha is the sigma alpha of capital I, and we have one minus modulus of capital I of zeta squared over something. Well, this expression alpha minus capital I of zeta modulus squared is sometimes equal to 0, but only on a small set. But just by the definition, the 1 minus modulus of I of zeta squared is equal to 0 sigmas almost everywhere. And well, just again, basic properties of the corresponding Poisson integral. Well, even for say M harmonic from Poisson integral, this is still true. Just in the unit disk, this is one of the basic facts about this measure, that this is a singular measure. So here in what follows, it means that it's singular with respect to Lebesgue measure, denoted by capital sigma in our case, and we use this notation. Okay, and well, singular part or absolutely continuous part of a measure will always mean with respect to Lebesgue measure, because well, we already have certain families of different measures. So all these sigma alpha are sometimes singular with respect to Lebesgue measure, sometimes they are say mixed. So all these terms, singular and absolutely continuous, always refer to the Lebesgue measure. So this is kind of specific case because, well, all these sigma alpha are singular measures. This is not always the case, but this is kind of extreme case. And initially, it was the most interesting one because it refers to the so-called model spaces, well, very useful spaces in the theory of in the operator theory. Well, in several variables, we still have certain analogs. So basic definitions here are so whole of omega, just the space of whole holomorphic functions on omega. So we also use the classical Hardy space, just the standard definition is in the unit disk. So the corresponding integral means of f of r zeta to the power p respect to Lebesgue measure integral over the boundary. We take the supremum over r from 0 to 1, and this supremum should be less than infinity. So this is actually the norm to the power p, or quasi-norm if p is less than 1. Also it is known that and we use this fact to identify this Hardy space HP of omega in general for p greater than 0, less than infinity. For h infinity, just this is the space of bounded holomorphic functions in omega. And we identify this space and the space HP of d omega on the boundary. This is the space of the corresponding boundary values. Well, they do exist. This is a known fact of this theory. Okay, and now if we consider in a function, and in this case I use again a different notation theta. This is standard one for the unit disk, and just to distinguish two situations of the unit disk and of several variables. So in this case, the model space k theta is the classical one. K theta is the standard notation. And this is defined as just the orthogonal complement of theta h2 in h2. So this is a Hilbert space, and this we take just the orthogonal complement. So Clark measures were introduced by Clark in 1972. Well, it's possible to probably to name other names around this date in 1972. Other mathematicians also considered and investigated and used these objects, but well, still, we consider, we assume that sigma alpha is a Clark measure, okay? So the main point for Clark was to consider a certain, say, I say here useful unit operators, but they are not just useful, but well, it's true. In applications, it's possible to deduce new results with the help of these operators. But in a sense, they are canonical. So these are operators, unitary operators between k theta onto, well, this is a unitary operator, onto L2 of sigma alpha. So somehow, instead of k theta, certain, well, space related to hard spaces and, well, certain orthogonal complement in H2, we just make allowed to consider just L2 space, but with respect to the specific measure for each alpha, this index, the number on the complex number on the unit, the point on the unit circle, they have just a different operator use of alpha, but still those operators are all unitary operators. Well, in general, this is not a big surprise. K theta is a Hilbert space, separable Hilbert space. L2 of sigma alpha is also a separable Hilbert space. But this is not like an abstract result. This is kind of explicit construction. And moreover, finally, it was Poltoratsky who is 1993 actually proved that those functions in K theta, so these unitary operators are the most natural ones. Just each function in K theta does have radial, even non-tangential boundary limits, sigma alpha almost everywhere, and this unitary operator, you just it's possible to define it as just the operator of taking boundary values, and in this case, it's clear that this is a unitary one, and it explains this that this is the most natural one. Well, in several variables, the situation is more complicated, but at least the first part, and in some cases of the Clark construction, still works. Okay, but the main issue here is just for an inner function capital I in the domain omega, there is no canonical way to define a direct analog of the space K theta. Well, I'll mention just the most obvious one. So we consider just the H2, this is just H2 omega. And the most direct analog is just again the orthogonal complement of capital IH2 in H2. Well, in a sense, it's reasonable to say that this is the large or the largest model space to consider. And if omega is the unit ball, then Clark's construction is extendable to this large model space. We do obtain natural unitary operators, and they are still useful in some situations, but, well, certain theory does exist. Well, we have obtained certain theory up to certain restrictions, but already in the power disk decay of dimension, or in bi-disk of dimension at least 2, in general, if we do extend the Clark's construction, well, in bi-disk, in general, we obtain only partial isometers, not unitary operators. It's possible to characterize when the operator obtained T sub alpha is indeed a unitary operator, but it is not always just a unitary one, only partial isometry. And, well, just to also to explain the differences and the difficulties here. So in the unit disk, there is no problem to give more or less explicit examples of inner functions, singular inner functions, Blaschke products, and so on. In the unit ball of dimension at least 2, this is not straightforward at all. Okay, all the examples are, well, completely inexplicit. Say, well, at least, well, it's difficult to get some explicit properties of inner functions. Well, sometimes it's possible just to obtain certain specific properties of the corresponding analogs of singular inner functions. Well, but on the other hand, the unitary operators T sub alpha are unitary operators. Okay, in the power disk, still to get an example of an inner function, it's not a problem. Well, say if we consider just rational fractions, rational inner functions, well, this is already a huge family, the rich one, and everything is fine. But well, the main issue that even for say such simple fractions, the corresponding operators are no longer unitary but only partial isometries. So this theory is more sophisticated. Okay, so just to mention other applications besides this main topic today of composition operators. Okay, so also a very useful result. Sometimes it just allows to reduce various properties to more simple problems, and also kind of say unexpected property, not only useful but also unexpected property. Each family of Clark measures, well, in English one says that each family disintegrates Lebesgue measure, and also in particular this is true for an inner function I, capital I, when each, as we know, each Clark measure is singular one. Still, when we integrate with respect to alpha, as we see below in the theorem, we say reconstruct the initial Lebesgue measure, the absolutely continuous one. Well, also in English literature, this theorem is in dimension one is often referred as Alexandrov's disintegration theorem. Okay, so in several variables we have a function p defined on domain omega and mapping into the unit disk. We have this holomorphic function. We consider the corresponding Clark measures, sigma alpha of p. Alpha is the parameter on the unit circle. So this, as I said before, just if we integrate with respect to this parameter, so with respect to Lebesgue measure sigma 1 on the unit circle, we obtain the normalized Lebesgue measure on the distinguished boundary d omega. Well, in the weak sense, of course, it means if we take an arbitrary function continuous on the distinguished boundary and we integrate. So on the left-hand side, on the right-hand side, we have functionals. So we apply both of these functionals to a continuous function, and then we have a true equality. Just every integral is defined. Well, in fact, it's not from the very beginning. It's not obvious that the first integral of f the sigma alpha. This one is defined, of course, but that what we obtain, this function is integrable with respect to Lebesgue measure. Well, this is a technical moment, but still, well, up to this, everything is defined. So the function is continuous. The right-hand side is just straightforward to define, and the right-hand side, the left-hand side is also defined, and just they have this equality. Just I'm not going to use directly this property, but just this is kind of, well, very good example how unusual this family is, each family of Clark measures. And well, in other applications, just exactly this property is very useful. Okay, so now I'm going to consider the main objects, composition operators. So still, I recall that HP is just the classical Hardy space. We have holomorphic function from omega to the unit disk. So it is well known that the corresponding composition operator, F composition with P, where F is an HP on the disk. It maps each function into from HP on the disk to HP of omega. And just to make sure, while this is a basic fact by now, it's not that obvious how to deduce it from the very definition with the supremum over R between 0 and 1. So, well, well-known short proof, it depends on the following property that if function is an HP on the disk, then modulus of f to the power p is estimated by a certain function that exists of a harmonic function h, such that h is at least this modulus to the power p, and then just be put inside phi, and we obtain the harmonic measurand for the new function f composition of phi. And well, again, this is still a characterization of HP in omega. So we see that each function in HPO on the disk goes to function after application of this, sorry, of this operator, goes to HP on the domain. Also, it is known that if we have function, the initial symbol holomorphic function p, if it is the corresponding operator is compact for some p, then this happens if and only if it is compact for all p greater than 0. Well, in the classical situation, there are some special proofs. Just probably I should mention that say the shortest proof probably comes from interpolation theory. I mean interpolation of bounded and compact operators. So once we have the operator is bounded on all HPs, from HP on the disk to HP on the omega, then it's possible to just interpolate compact operators and bound it and to extend compactness to all parameters p. Probably this is the shortest way to show this. Okay, so what's the main theorem? So I should at least formulate this result. So it's possible to relate the say measure theoretic properties of the Clark measures in the operator theoretic properties of the composition operators we consider. So still we have phi holomorphic function from omega to the unit disk, then it's possible just to compute the essential norm of the composition operator, and in particular, this will be the corollary. So once we have this just explicit expression for the essential norm, we also characterize the compact operators, compact composition operators. In the case of one variable, it was kind of, well, certain history of several results. I'll mention this history somewhat later as a motivation. But well, the main theorem here is the parameter p is equal to 2, and we consider composition operators from H2 on the disk to H2 on the omega. So once phi is defined, maps omega to the disk, then the composition operator just say, in a sense, x in reverse from H2 on the disk from to H2 on the omega. So the essential norm is just the square root of the supremum of the norms sigma alpha s. Alpha goes over the unit circle. S means that we consider not the whole Clark measure, but it's singular part, and as usual, a singular part with respect to Lebesgue measure. So, I'll say a few words below later about the proof, and to simplify the notation, I will assume that omega is just the unit ball, and well, in this case, instead of capital sigma, the normalized Lebesgue measure on the distinguished boundary, I'll use the notation capital sigma sub n, again for the normalized Lebesgue measure on the unit sphere. Okay, so this is the main result. In dimension 1, this result was obtained already more than 20 years ago, but well, several variables, it's relatively new. It was published in 2020. Exactly this result. No, I mean just for the unit ball. Okay. So about the proofs, So the one of the main technical tools are so-called nonlinear counting functions, and exactly these functions were used by Joel Shapiro in 1987 to obtain the final solution of the corresponding problem in dimension 1. So the main idea is that we have the very classical little Pele identity. Well, what was proved approximately a century ago. So if we compute, well, everything now is about H2, because in H2, well, this is a Hilbert space, and we obtain exact value for the corresponding essential norm. In fact, if P is arbitrary, is not equal to 2, then still an analog of the main theorem holds, but we have no equality, but just certain estimates. So this is why I prefer to, even in the days, and I prefer to formulate the separately theorem when we have just explicit identity. So the essential norm is equal to. Well, probably I should just mention briefly that essential norm means norm up to, say, compact operators. It is allowed to decrease the norm with the help of compact operators. So one of the definition of the essential norm, say. Okay, so this is why this is, well, initially for Joel Shapiro, the initial question was just to characterize compact operators. And well, of course, if we have a formula for the essential norm, then the operator is compact if and only if the corresponding expression is equal to 0. Okay, so in the case of Joel Shapiro, so he used this so-called nonlinear counting function and the corresponding expression based on this function to obtain a different expression. Well, in fact, main theorem is a particular case of a more technical result, a more general result with two parts. It's possible to compute the essential norm in terms of the nonlinear counting function or in terms of the Clark measures. So main theorem is related to Clark measures because the Clark measures are the main objects today. But well, still, so the idea is to replace this Littlewood-Pele classical identity by a similar formula with when we use the nonlinear counting function. This is a function defined as the sum of log 1 over modulus of z. So we take n sub phi of omega of w. So phi of z should be equal to w. So we do not count zeros, so in plus infinity. So we exclude. We assume that omega is in the disk minus phi of 0. So, and also we count this, we have a sum and we count it with multiplicities. So everything is defined. Once we have excluded, we consider omega such that omega is not equal to phi of 0. Okay, and then the formula in our case, just for n equal to 1, this is actually a Stanton's formula, well, more or less directly used by Shapiro, and then he just did the rest, say, okay, somehow Stanton did generalize the Littlewood-Pele formula, but he didn't realize that, well, it is applicable, this formula is applicable to composition operators, say compact composition operators, and more generally, essential norm of such operators. So just as in the case of Formula 1, Littlewood-Pele identity, we just replace now F by F composition of phi, and then everything is the same except, well, we replace, it was just log 1 over modulus of W, Now it's reasonable to expect that we have to replace it by the Nevalin counting function. Okay, if n is equal to 1, then just there is no integral over the sphere dBn. This is just the Nevalin counting function. If we have several variables, then this additional integral appears. And well, this is a technical moment, but well, this is somehow, just to explain this point, we have a unit ball, and somehow it's a standard object. If you have phi defined on the unit ball, the slice function is just for each point zeta on the sphere. We consider f sub zeta of lambda. This is phi of lambda zeta. Okay, this is a function already defined on the disk, so holomorphic self map of the unit disk. So somehow, informally, this formula 2 explains how to integrate compactness by slices. Okay, well, this is very informal, but this is how it works. Well, when we write formulas, it works like that. Okay, and well, what's the difference between formulas 1 and 2? So in the classical Littlewood-Pella identity, we have log 1 over modulus of W. This is equivalent actually to 1 over 1 minus W, when W is close to the boundary. So, well, for compactness, it's natural to expect that the operator will be compact when the corresponding integral in this case, or just in the case of the unit disk, just the Nevalin counting function divided by 1 minus modulus of W. The corresponding lim sup as W goes to the boundary is equal to 0. So compactness corresponds to boundedness, corresponds to estimate with a constant. This is always true for the Nevalin counting function. For compactness, should go to 0. So when we compute the corresponding lim sup. Well, this is indeed the case, and the main theorem here is the following one. So let capital E of phi denote the essential norm we consider under consideration. Then the main technical and the more general result is the following one. In the case of in the Hilbert case, in fact, the essential norm squared is equal to S of phi, where this is just the supremum in terms of the singular parts of the Clark measures, and also it is equal to n of phi, the corresponding expression in terms of the Nevalin counting function. So when n equals 2, the equality between E squared and n was obtained by Joel Shapiro. Later, 10 years later, Sima and Matheson proved that actually they used one part of Shapiro's result, that E squared is equal to this S, the main object of interest for us in terms of Clark measures. Well, actually, it happens that it's possible to, well, in particular in dimension 1, but for us it was of interest to get the result in several variables, to get through, say, 2 proofs and to get all the necessary estimates. Say, the plan of the proof is very simple. We start with E squared. This is greater than or equal to S, greater than or equal to N, and again, greater than or equal to E squared. So we have equalities everywhere. And this is the result. So more or less, I should stop here. So I'll mention just the corollary. So as I said before, for arbitrary parameter P, still, if we consider just, we are interested only in compact operators or even in estimates for essential norms, well, the corollary is given for just compact operators. Okay, the operator is compact if and only if the corresponding Nevalin counting function expression is equal to 0. or just all Clark measures are absolutely continuous. This is just straightforward for p equals 2. And once we know that the compactness does not depend on the parameter p, then we obtain the result for all p greater than 0. If you want estimates for essential norms, then we just basically modify the proof for the Hilbert case, and well, it works. Okay, thank you.
Thank you for a very nice talk. Let us thank the speaker. Now we have time for questions. First questions to Professor Doubtsov, and then questions to Professor Shkalikov. Please. Okay, then I have a question. From your point of view, what is the most interesting result in your talk?
Well, basically, the main theorem is as it was mentioned. Well, I mean, the most interesting part is that such result indeed exists in several variables. Okay. Well, still, in terms of Clark measures, well, basically, somehow, if we use Nizhny accounting function expressions, they are somewhat inexplicit already in the disk. In several variables, they are even more inexplicit. But well, somehow it is considered that once we have a mapping, say, homomorphic self-mapping, or even on the unit disk, so to consider this mapping and its Clark measures, it's all the same, just in different terms only. So this is the most explicit characterization once we use Clark measures. And also somehow the proof goes through 3 estimates. So we do not prove separately equalities for essential norm and Nizhny accounting function, and essential norm and Clark measures. So everything is together. So this is the main point probably. So as a result, just the main theorem. Okay.
Thank you. More questions to Professor Doubtsov? No questions? Okay, then let us thank the speaker again. Very nice talk.